Hey everyone! Stack lessons here. Chunking strategies and embedding context length trade-offs trips up a lot of students, so today we're going to make it crystal clear. Let's go! By the end of this video, you'll be able to size a chunking pipeline without blowing your vector database capacity, pick the right chunking strategy for any document type, and match an embedding model to your chunks without overpaying for context you'll never use. You'll also know exactly why DataDino's first 2 attempts failed, and how the chunk count math would have caught both before a single vector got stored. Quick context. Last episode, DataDino's 40,000 pages landed in a Delta table as clean extracted text that was the bronze ingestion pipeline. Now that text has to become something a vector index can actually search, and the step in between is chunking. It's where retrieval quality is won or lost. 3 terms anchor the next few scenes. A chunk is a contiguous piece of a document, sized to fit inside an embedding model's context window. Overlap is the number of tokens that get repeated between adjacent chunks, so a sentence doesn't get amputated at the boundary, and embedding context length is the maximum input the embedding model will accept. Anything past it is silently truncated. We'll introduce dimensionality and change data feed later, when they actually come up. You built a RAG pipeline. It retrieves the wrong clause every single time, and the fix is not the model, it's how you cut the text. DataDino lived through exactly this. Twice. Their first chunker was the simplest thing that could possibly work, a fixed-size character splitter with no overlap. It cut one of their fossil taxonomy entries clean in half, between the genus and the species name. Retrieval precision collapsed, so the team overcorrected. They jumped to 2048 token chunks, and silently maxed out their embedding model's 512 token context. 3/4 of every chunk was being truncated before the model ever saw it. 2 failure modes. 1 missing skill, the chunk count math and the embedding context math that this episode is going to give you cold. Chunking exists because 3 constraints have to be satisfied at the same time. The chunk has to fit inside the embedding model's context, or the tail gets truncated. It has to fit inside the LLM's context at query time, alongside several other retrieved chunks, and it has to represent one coherent idea, because a vector is supposed to mean something. Half a sentence plus the start of a new topic doesn't mean anything an embedding model can usefully encode. The Databricks documentation puts it cleanly. Segmenting large documents into smaller, semantically concentrated chunks ensures retrieved data fits in the LLM's context, while minimizing distracting or irrelevant information. Notice the 2 jobs in that one sentence: fit the context and filter the noise. Those are the goals every chunking strategy is trying to balance, and the strategies differ mostly in how they trade one against the other. 6 strategies. 1 job. We're going to walk each one in order, what it does, when it's the right pick, and which DataDino problem it solves. Just the names for now, so you've got the landscape. Fixed size with overlap is the baseline. Recursive splitter is the production default. Sentence and paragraph aware respects linguistic boundaries. Semantic chunking breaks where meaning shifts. Window summarization carries prior context forward, and section header prefix prepends the document hierarchy. We'll take them one at a time. Start with the simplest one. You take n tokens, you slide forward by n-m, you repeat. That's the entire algorithm. The overlap m exists for exactly one reason: to stop a sentence from being amputated at the boundary, the way DataDino's first chunker did. Fixed size is fast, deterministic, and it's the only strategy where chunk count is genuinely easy to predict, which is why the chunk count math we'll do later uses it as the reference. A common starting point is between 200 and 500 tokens per chunk, with overlap around 10% of the chunk size. But the Databricks docs emphasize matching chunk size to your embedding model's token limit, and validating retrieval quality for your specific use case. A 500 token chunk is roughly 1 page of text, a handy mental conversion. The recursive character splitter tries a hierarchy of separators, in order. The default list is paragraph break first, then single line break, then space, meaning word boundary, and finally individual character. Notice there's no dedicated sentence separator in that default list. If you want sentence-aware splitting, you have to add it yourself. The splitter only falls back to a finer separator when the current chunk is still too big. LangChain's recursive character text splitter is the canonical implementation, and Databricks documentation lists it as the go-to option for paragraph-based chunking in production RAG, noting that plain character count splitting rarely works for production-grade applications. Think of slicing a pizza. You use the pre-cut lines first, then you cut between toppings, and you only cut through a pepperoni if you absolutely have to. One detail catches almost everyone. The chunk_size parameter is in characters by default, not tokens. Set it to 2000 expecting 2000 tokens, and you've actually built chunks 4 times too large, which then truncates silently on the embedding side. Sentence and paragraph-aware chunking uses something with linguistic knowledge, the Natural Language Toolkit, sparse-I, or even a careful regex on punctuation, to find real sentence boundaries. Chunks always end on a complete thought. This is the direct, targeted fix for DataDino's first failure. No more splitting a taxonomy entry between the genus and the species, because the chunker now knows where a sentence actually ends. It's slightly slower than fixed size, but at the document volumes we're talking about, the precision win is essentially free. Semantic chunking is the most ambitious approach. You embed every sentence individually, then walk through the document measuring how similar each sentence is to its neighbor. As long as the similarity stays high, you keep adding sentences to the current chunk. The moment similarity drops below a threshold, like the jump from 0.88 to 0.32 on screen, that's your boundary. The result is a chunk where every sentence is genuinely about the same thing, which is exactly what an embedding model is supposed to represent. The cost is real, though. You're running an embedding model just to do the chunking, before you've stored a single vector. Worth it when retrieval quality is the bottleneck, overkill when it isn't. Window summarization is the long document fix. Each chunk gets a short summary of the chunks that came before it, prepended as a prefix. The summaries are generated by an LLM in a sliding window over the document at indexing time. Think of the previously on recap at the start of a television episode. You can jump straight into episode 7 and still follow the plot, because the recap carries the relevant history forward. Same idea here. Retrieval can drop the LLM into chunk 47 of one of DataDino's long stratigraphic reports, and the model still has the running thread of the document. It costs an extra LLM pass at indexing time, but indexing is offline. You pay that cost once. Here's the research finding that makes window summarization matter. Transformer models pay disproportionate attention to the start and end of their context, and information sitting in the middle gets quietly underweighted. This is the lost in the middle effect, and research has traced it to specific attention patterns, meaning it's structural, not just a training quirk. Bigger context windows don't make it go away. Window summaries fight back by pulling the earlier narrative into every chunk's prefix, where the model actually attends to it. Section header prefix chunking prepends the hierarchical path to each chunk before embedding. Something like the document title, then the section, then the subsection, in brackets, followed by the actual body text. That path lives both in the chunk text, so it gets embedded, and in the chunk's metadata. It's the right strategy for any document where structure is part of meaning. HR policies, contracts, regulatory filings, and DataDino's stratigraphic reports all qualify. Like writing the return address on every page of a letter. If the pages get shuffled by retrieval, anyone can still tell which envelope they came from and which chapter they belong to. Here's why this matters in practice. Take a long master services agreement with 2 clauses that both happen to read the term is 3 years. Without the prefix, the chunker stores chunk A and chunk B with nearly identical text. Their embeddings sit on top of each other in vector space. Retrieval can't tell warranty from limitation period, and the chatbot confidently answers the wrong clause. Now add the prefix. The first chunk becomes MSA, warranty, coverage. The term is 3 years. The second becomes MSA, limitation period. The term is 3 years. The embeddings now separate cleanly, and the right clause comes back for the right question. No embedding model swap required. 6 strategies, each one matched to a document type. From here, the rest of the episode is numbers, the chunk count math that decides chunk_size and overlap, then matching an embedding model to that chunk size. Here's the scenario. Your pipeline produces 150 million chunks. Your vector database tier caps at 100 million records. Budget is fixed, so moving to a larger tier is off the table. Which 2 configuration knobs actually reduce the row count? Most engineers reach for the wrong knob here. Let's derive the right answer from first principles. Here's the formula. Record count is approximately total tokens divided by chunk size minus overlap. The numerator is fixed. That's just how much text you have. The denominator is what you control. Every chunk advances through the document by chunk size minus overlap tokens, because the overlap repeats material from the previous chunk. To reduce the record count, you need to make the denominator larger. That's the whole game. 2 moves are correct. Increase chunk_size, the denominator grows, so the record count shrinks. Decrease overlap, same effect, the denominator grows. Both work, and the only quality cost is that your chunks become a little coarser. Now the moves that go the wrong direction, which are the ones most people reach for. Decreasing chunk_size makes the denominator smaller, which gives you more rows, not fewer, the opposite of what the scenario needs. Increasing overlap does the same thing. And the sneakiest distractor, switching to a smaller embedding model, sounds plausible but changes the dimensions per row, not the number of rows. The capacity limit is about row count, not bytes. If the algebra slips, fall back on the picture. You're packing a moving truck. You've got space for 100 boxes, and you've got 150 boxes of stuff. You can't buy a bigger truck. The budget is fixed, so you use bigger boxes, which is increasing chunk_size, and you stop wrapping every item in 3 layers of bubble wrap, which is decreasing overlap. Smaller boxes and more bubble wrap make the problem strictly worse. That's the direction you never want to move. Now to the second piece of math, embedding context length. This is a hard cap on input tokens, and anything past it is silently truncated. No error, no warning. All mini LML6 v2 caps at 256 tokens, and it was actually trained on sequences of up to 128, so quality starts degrading well before you hit the cap. BGE large goes up to 512, GTE large version 1.5 jumps all the way to 8192. This is exactly what bit DataDino on attempt 2. Remember, the recursive splitter we walked through earlier would have fixed their first failure, the genus-species split, but it wouldn't have caught this one. They pushed 2048 token chunks at a 256 token model and lost the vast majority of every chunk before it was ever embedded. The discipline here is to match the model's context to your chunk size. That's a fit requirement, not a quality dial. Here are 4 candidate models for a 512 token chunk where cost and latency dominate. Option 1. A 512 token context, about 1.27 gigabytes, 1024 dimensions. Think BGE large. It fits, but it's heavy. Option 2. 2048 context, 11 gigabytes, 2560 dimensions. Massive overkill for 512 token chunks. Option 3. 32,000 context, 14 gigabytes, even more overkill. Option 4. 512 context, just 130 megabytes, 384 dimensions. That's the answer. It just barely fits the chunk size. and it's a fraction of the cost and latency of the others. The rule is, smallest model whose context covers the chunk wins. The instinct to reach for the biggest embedding model is wrong, and the production data is brutal about it. Teams have reported cutting vector database storage costs by more than half, and query latency by roughly 40 to 75%, by dropping from 1,536 dimensions down to 384, often with minimal impact on retrieval quality for domain-specific tasks. Like buying shoes, you don't grab a size 14 boot when you wear a size 9. Extra capacity you'll never use just makes you slower. Here's the distinction that keeps these two levers straight. The embedding model controls dimensions per row, 384, 768, 1024, 3072. That drives bytes per record, search latency, and storage cost per million vectors. The chunking strategy controls the number of rows themselves, how many records end up in the index, whether you blow past the capacity ceiling, and how cleanly each row means one thing. Two completely different axes. When the requirement is to reduce record count, only the chunking axis matters. When the requirement is to cut storage cost or latency at a fixed row count, that's the embedding axis. Strategy, chunk size, overlap, and embedding model are all locked in. One piece left, getting these chunks into a delta table in a way that vector search can actually consume. Two pieces of code. First, write the chunks data frame to a delta table using the three-level name, catalog, schema, table. For DataDino, that's datadino.rag.fossil_chunks. The three-level name is what puts the table under Unity catalog governance. Second, and this is the line that matters, alter table, set TBL properties, delta.enable change data feed equals true. That single property flip is what turns this delta table into something vector search can incrementally sync from. Without it, the next step doesn't work. Straight from the AI search documentation, for standard endpoints, the source table must have change data feed enabled. Not should, not preferably, must. If you forget this property, the delta sync index will fail to create, and even if you patch it on after the fact, the incremental sync only works for changes recorded from the moment CDF was turned on. Think about CDF as a hotel housekeeping log. Instead of cleaning every room every morning, housekeeping reads the log of which rooms were checked out overnight, and only services those. CDF is that log for your delta table. Vector search reads it and knows exactly which chunks were inserted, updated, or deleted since the last sync, and only re-embeds those. Turn the log off, and the sync job has to redo every chunk, every run. That's a cost difference of orders of magnitude on a 40,000-page corpus. One last thing before we wrap. DataDino's chunks are now sitting in a delta table with change data feed enabled, production ready as far as chunking goes. The next episode opens up Mosaic AI vector search itself, the delta sync index types, the managed versus self-managed embedding modes, and the storage-optimized endpoint tier we touched on in episode 1. Every retrieval decision from here on out is built on the chunking decisions you just made, so the math sticks with us. 4 decisions, always in this order. First, pick the strategy by document type. Structured documents get section header prefix, long narrative documents get window summary, and recursive is the default for everything else. Second, pick chunk_size and overlap by vector DB capacity. Too many rows means increase chunk_size and decrease overlap, never the other direction. Third, pick the smallest embedding model whose context length is greater than or equal to your chunk size. When cost and latency dominate, 384 dimensions at a 512 context almost always wins. Fourth, enable change data feed on the chunks table. That's non-negotiable for delta sync index. 3 knobs and 1 switch. Knob 1 is strategy, picked by document type, not by gut feel. Knob 2 is chunk_size and overlap, the only two levers that actually move the row count. Knob 3 is the embedding model, where the smallest context that fits your chunk wins on cost and latency. And the switch, delta.enable change data feed equals true. Without it, vector search can't sync. Now let's see how well you absorbed all of this with a quick 5-question quiz. Alright, time to put your knowledge to the test. Question 1. A RAG pipeline has produced 150 million chunks, but the vector database tier caps at 100 million records, and the budget is fixed. Which two configuration changes will reduce the record count? Is it A, decrease chunk_size and increase overlap, B, increase chunk_size and decrease overlap, C, switch to a smaller embedding model with fewer dimensions, or D, increase chunk_size and increase overlap? Take a moment to think about it. The answer is B. Record count is approximately total tokens divided by chunk_size minus overlap. Growing the denominator is the only way to shrink the row count, and that means a bigger chunk_size and less overlap. A smaller embedding model changes dimensions per row, not row count. That's the trap option. Question 2. An HR policy chatbot using a recursive character splitter and a standard embedding model returns fragments like annual leave is 20 days without context, so users can't tell which policy section the answer comes from. Swapping the embedding model and the LLM did not help. What is the most effective fix? Is it A, switch to a larger embedding model with an 8192 token context window, B, decrease chunk_size and increase overlap to capture more context per chunk, C, adopt section header prefix chunking so each chunk carries its document hierarchy, or D, replace recursive splitting with fixed size character splitting? Take a moment to think. The answer is C. When two policy sections both say something like the term is 20 days, their embeddings end up nearly identical and retrieval can't tell them apart. Prepending the hierarchical path puts discriminating context into both the embedded text and the metadata. Swapping models doesn't fix a segmentation problem. Question 3. A team is chunking documents into 512 token segments, and cost and latency matter more than absolute retrieval quality. Which embedding model is the best fit? A, 514 token context, 0.44 gigabytes, 768 dimensions. B, 2048 token context, 11 gigabytes, 2560 dimensions. C, 32,768 token context, 14 gigabytes, 4096 dimensions. Or D, 512 token context, 0.13 gigabytes, 384 dimensions. Take a moment. The answer is D. The smallest model whose context covers the chunk wins on cost and latency. The 512 token context model at 0.13 gigabytes and 384 dimensions fits the chunk almost exactly and is dramatically lighter than the alternatives. The larger context windows are unused capacity, not extra quality. Question 4. An engineer writes a delta table of chunks to Unity Catalog and tries to create a vector search delta sync index against it. The index creation fails. What is the most likely missing step? A, setting delta.enable change data feed equals true on the source table. B, re-embedding all chunks with a model that produces 1024-dimensional vectors. C, switching to a two-level table name without the catalog. Or D, enabling Photon on the workspace before index creation. Take a moment. The answer is A. Delta sync index requires change data feed enabled on the source table so the sync job can read row-level inserts, updates, and deletes incrementally. The official AI search documentation states this as a hard requirement. Without CDF, index creation fails. Question 5. A team is chunking a 300-page stratigraphic report where conclusions on later pages depend on definitions and cite context established in the opening sections. Which chunking strategy best preserves that early context when retrieving from deep in the document? A. Fixed size character splitter with zero overlap to keep chunks uniform. B. Recursive splitter tuned to a small chunk underscore size so more chunks fit in the index. C. Window summary chunking, where each chunk carries a rolling summary of the document so far. Or D. Semantic chunking driven purely by embedding similarity boundaries. Take a moment. The answer is C. Window summary chunking attaches a rolling summary of prior content to each chunk, so a chunk retrieved from page 200 still carries the definitions and cite context established at the start. Fixed size and pure semantic chunking lose that long-range context, and a smaller chunk underscore size only changes how the document gets sliced. It doesn't carry early context forward with later chunks. And we're done with chunking strategies and embedding context length trade-offs. If this saved you a wrong answer on exam day, hit subscribe. The Databricks GenAI Engineer cert keeps going, and I want you to pass on your first try. See you next time.